Another type of application problem I want to do with vectors is a tension problem. And a tension problem is one in which we use vectors to represent the magnitude of the pulling force that is exerted by a cable or a rope or some other object that might be holding up some type of weight or mass. And it's important to understand here that the magnitude of these vectors are going to represent the force that is exerted by the cable. It is not the length of the cable itself. It represents its pulling force. One other thing that I want to mention about these systems is the idea of the static system, which is when the system is in equilibrium and not moving. So it's when the amount of force that is exerted by the cable is equal to the force that is weighing that cable down so that it's not moving. If it's not in equilibrium, then you have the object actively being pulled up or that object actively pulling that cable down. But when it's in static or when it's a static system, then the cables are not moving themselves. And when this happens, the sum of the forces in the horizontal and vertical directions is equal to zero. And I think it's best if I just dive right into the problem so you can see this laid out in full with actual values and numbers and vectors actually drawn out. So let's go ahead and try this first problem here. So we're going to use a figure. We're going to draw our own figure to determine the tension in each cable supporting the load. And you're not given any words written out here. I'm just going to go ahead and draw the diagram so we can see the system. So suppose you had some type of beam, or let's say just attached to the ceiling itself, okay? And we've got two different points or two different places where we have cables. So we have point A and point B. And let's just say that this is our first cable, cable A, and we have cable B here, okay? And from this point at the bottom, these cables are holding up some type of object. And let's just say that the object weighs, let's say 1,000 pounds. Let's just say that, 1,000 pounds, okay? So we've got a cable and it's holding up an object that's 1,000 pounds. And if I were to draw a vertical up and kind of straight up from wherever the weight is, I could say that this distance here from point A to this point that's directly above the weight is 5 feet. Suppose this were 5 feet. And from point B, where the cable is attached to the ceiling or to the beam, this distance were 3 feet, okay? And because the weight is being held straight up, we're going to say that both sides are going to represent a right angle. And the final bit of information I should probably tell you is that let's just say the distance from here to here is 5 feet as well. So this vertical distance here is 5 feet, okay? So we have right now, this is a system. These are with the physical cables. What you're seeing here are the actual cables A and B that are holding up this weight. This is not a vector diagram. To be clear, I've not drawn a vector diagram. I've just drawn a diagram that represents this system as I'm describing it. And what I want to first start with doing is finding these angles here, because we're going to need these when we draw our vector diagram. So theta A and theta B. So the first thing I'm going to do is I'm going to find these angles. So find the angles. I'm going to label out my steps. So theta A is simply going to be what? And just think about this for a second. How would I be able to find this angle? And the correct answer is using trigonometry. We can say that theta A is the inverse tangent of my opposite over my adjacent, or 5 over 5. And we don't need a calculator to know that this is going to then be 45 degrees, right? And when our opposite is equal to my adjacent, then we have a 45-degree angle. Theta B would then be the arctangent, this time of 5 over 3. And this one we probably do want to punch into our calculator. We will get 59.036 degrees. So we've just found our angles. The next thing I want to now do is I want to now set up a vector diagram. And again, to be clear, I have not drawn a vector diagram just yet. All I've done is just a diagram to describe the system as with the actual cables and the weights. But now I want to draw a diagram that shows the vectors. So it's going to look pretty similar initially. So we still got a vertical line, we still got the weight down here. But, so we're going to draw this. We're going to say this is our point C, and point C to D, that's going to be a weight. So this represents this portion here of the diagram, okay? And this is a vector C going to D, and this vector has a mass or a force of negative 1,000 pounds, okay? Now, let me just kind of zoom out so you can see both things going on here. Now, it's important to recognize here that what we have is vector A, C going to A. So I'm going to draw that. I'm going to draw that vector here, C going to A. So there's C going to A. And I'm going to just label that here. That's vector CA, okay? I also have a vector C going to B. Now, I'm going to draw this vector a little bit longer here because of this key fact. These vectors, their magnitudes are the force. Their magnitudes are the actual tension. You'll notice here that if my cable is shorter, then I would actually have more tension exerted on that cable. The longer the cable is, then the less amount of tension I would have. So since the cable B going to C or C going to B is a shorter cable, it should have more tension. Therefore, it should have a larger magnitude. So that's why I'm drawing this vector C going to B as having a longer magnitude. And so what I would then draw, C going to B, I would add it to CA. And why am I adding it? Because this system is in equilibrium, as I mentioned earlier. It is a static system, meaning these should be equal to one another. So another way of expressing that is to say that's vector CA plus vector CB plus vector CD. All three of these vectors need to be equal to 0, okay? All three of these vectors need to be equal to 0. So what then I can draw with that fact is the following. Vector CB, I can then draw up here as such. This is the same vector CB. And you know what? Instead of just calling these vector CB after a while, let's actually just go ahead and let's relabel these. Let's just say let TA represent the tension of vector CA, and let TB will represent the magnitude or the tension of CB, and we'll get to that in a second. But I can draw CB back up here. So this right here is vector C going to B, okay? Now, what do we know about these vectors? Well, the information that we found out with the angles theta are still going to apply here, meaning, and let me just do this in a different color, this angle that we found for theta A, that's still going to be equal to 45 degrees. This is still a right angle, meaning this angle here is got to be 45 degrees. Well, what do we find for theta B? Theta B, this angle here, or this angle here, theta B, we said that's still 59.036 degrees. Well, that is going to be an alternate interior angle with this angle here. So we see that those angles are congruent. And by transposing that vector over up here, that means this angle here is going to be 59.036 degrees. Remember, this angle here and this angle here are congruent. This angle here and this angle here are congruent. So we're able to draw that. Now, final bit of information, we know that since this vector CD is exerting a force of negative 1,000, in other words, its magnitude is negative 1,000, that means in order for this system to be in equilibrium, this here has to be positive 1,000. It's got to be exerting the opposite force. So this right here, this resultant vector has to be exerting the opposite force of 1,000. And if you look carefully at what we've just drawn here, I can actually just highlight, and let me actually just make that a little bit thicker so we can see. I can highlight here, what do we have? We have an oblique triangle. And let me just redraw that triangle up here. So let's just kind of draw this here. We have an oblique triangle right now with the following information. We know that this angle here is 45 degrees. We know that this side length here is 1,000. we know this angle here is the sum of 59.036 and 45 degrees. If we add that up, we should get 104.036 degrees. And also now using the triangle sum theorem, or just knowing that the sum of all my angles have to be equal to 180, I can subtract 45 and 104 from 180, and we should get 30.964 degrees. So I've got a triangle right now with all three angles and one of the sides. And I'm going to label the magnitude of vector CA as this is my tension of vector CA, and this is the tension or magnitude of vector CB. All I have now is an oblique triangle where I'm given three angles and a side, and I can use either the law of sines or the law of cosines to solve for my remaining sides. Well, given that I have two angles at a minimum and a side here, it would make more sense to now use the law of sines to finish solving this system or solving this triangle. So we're going to say, use the law of sines. So setting up the law of sines here, let's set up what we know. We know that the side length of 1,000 over the sine of 104.036 is going to be equal, that ratio is going to be equal the tension of vector CA over the sine of its opposite angle, which was 30.964. Send that out. And that's equal to vector TB, or excuse me, the tension of vector CB, or what we say T sub B, over the sine of 45 degrees. So from here, you can solve it in any number of ways. You can just say TA is equal to 1,000 sine of 30.964 cross multiplying, should put that symbol there, divided by the sine of 104.036. And when you put that into your calculator, you should see that the tension of cable CA should be approximately 530, 0.330 pounds was our unit. That's how we were measuring our tension. TB, T sub B, would be equal to 1,000 sine. And again, I always recommend going with what we were given if possible. So 1,000 times sine of 45. Oops, already wrote down sine. 45 over sine of 104.036, and T sub B should be approximately 728.869 pounds. So let's express our answers in sentences. So we'd say the tension of cable CA, C going to A, is approximately 530.330 pounds. And just for the sake of time, I'll just bring that over. The tension of cable CB, or C going to B, is approximately 728.869 pounds. So this is a great problem because it uses both vectors and our understanding of vectors, as well as the law of sines to measure the tension of a system that is a static system with tension.